Okay, hello guys. So this is the third part of my lecture on chapter number 9, and in the last lecture we had discussed about contingent assurances. Now I start with a new topic that is called as reversionary annuities. Okay, so these are basically annuities that are dependent on the order of death of two people. So immediately what comes to my mind is that example that I had started this chapter with. That example where there was a man X and he had a wife Y, and this man he went to a war, right? And this wife had no income source. Okay, she was not financially independent, so she was not financially independent. Okay, so now that this guy is in war, this wife, she basically wants financial security for herself. So if in case this guy dies, okay, as soon as dies, for her entire life, she wants annual payments or maybe monthly payments or some sort of annuity. Okay, so I'm gonna write annuity. Okay, so that is what we desire under such contract. So now what are the characteristics of such a contract? Let's try to list them. Okay, so what I want is let's try to make a number line and then decide what we exactly want. So it has to be a perpetual infinite term contract, right? From time 0 to time infinity, right? So at some arbitrary time t, I want that x dies, and that is when my annuity will start paying off, right? I want X to die at this time, right? He has gone to a war and he's fighting a war and he died, and at this time I want Y to be alive. So Y is alive at this time. That's something I want. And then I want to pay a certain amount to Y every year, okay, or maybe every month or continuously in form of an annuity. Let's consider the continuous case first, like we did in the case of assurance contracts. So I want to pay Y a continuous regular income. Okay, so Y would be receiving a continuous regular income till her death. Okay, so this amount would be paid from the death of X to the death of Y. Okay, so that's some conceptual clarity that we have here. And this would only start if Y is alive at this time, right? So at time 0, life aged X and Y are buying this policy, and this life aged Y should be alive at this time, and then from the death of X to the death of Y, she would be receiving these payments, right? In order to make her secure. So if I talk about the present value random variable for this simplest contract, that is my first concern. Okay. So what would be the present value random variable? See, uh, this would only happen if Tx is less than equal to Ty, right? Because I want X to die before Y. If Ty dies, Tx is greater than Ty, then nothing would be payable, right? So sure. So I want this payment to occur. So what is the amount of this payment? See, this payment, if you see it from here to here, it can be modeled as a continuous annuity. But what is the term of this annuity? The term would be the lifetime of Y minus the lifetime of X, right? Because it is starting to pay as soon as the lifetime of X gets over, and from time 0, obviously from this particular time. So as soon as the lifetime of X gets over, it starts paying, and it pays till the end of the lifetime of Y. So it becomes a continuous Ty minus Tx, right? In case, uh, obviously Ty has to be greater than or equal to Tx. And this factor, since it's payable from here, it has to be discounted till time 0. So there is a factor Vtx multiplied with it in order to discount it from the death of x to time 0. So this just becomes V to the power of Tx into a continuous Ty minus Tx, right? So that is my present value random variable. Okay, so this is one way of writing this present value random variable. There are basically two other ways of doing this. So the other ways are, in order to express this in this can be expressed in two other ways. So they are, one way you can write this present value random variable is as v to the power of tx remains same, a continuous, maximum of ty minus tx comma 0. Okay, so let's look at what this is saying. See, this is saying, this is actually this entire thing expressed in one term. Okay, if you want to express this in one term, this is how you can do it. Okay, so basically this is saying v to the power of tx, that is here, a continuous, maximum of ty minus tx. So if ty minus tx is greater than 0, that implies that ty is greater than tx, we can basically use this term. Okay, and if ty minus tx is less than 0, if this is less than 0, that would imply that ty minus tx is less than equal to 0, which would imply that ty is less than equal to tx. Okay, so when ty is less than equal to tx, that means it is a continuous maximum of 0, which just becomes 0. So this entire thing becomes 0, right? Because we know that a continuous of 0 is equal to 0. So this entire thing becomes 0. So this is how you can actually express in this thing in terms of a single term, right? So that is something you should know. Okay, let's just erase these things here so we have a clarity. So this is the second way of writing this present value random variable. Now there is a third way too. Demonstrating these, since they have given it in the book, although you don't really need them in the exam, you just they often give a few questions on present value random variable, so that is where you need these. They ask you to calculate net future loss random variable, so that's when you need these. Okay, so the third way is this is written in a similar way, it's just that this term is transformed a bit. So what we have here is, let's just see, we have got v to the power of tx into a continuous ty minus tx, right? So what can I write this as? I can write this as v to the power of tx into 1 minus v to the power of ty minus tx upon delta, obviously force of interest, since this is continuous. So this can be written as v to the power of tx minus v to the power of ty, so multiply it inside, upon delta, which can be written as 1 minus v to the power of ty upon delta minus 1 minus v to the power of tx upon delta. So 1 and 1 would cancel and you would get basically the same thing, which is the same as a continuous ty minus a continuous tx. So this is also one way that they have used in demonstrated in the core reading. So you can also write this as a continuous ty minus a continuous tx when ty is greater than tx, and 0 when ty is less than equal to tx, right? So that's something you can do. Okay, so these three conditions, they are the same and they are an expression for the present value random variable. Okay, let's talk about the expected present value of this contract. Expected present value, if we call this present value random variable as z, the notation that they have used, z continuous, we can call the expected present value as the expectation of z. Okay, so how will you basically calculate this? Again, this would be calculated in terms of an integral, obviously. So this becomes, what was the condition? See, the condition was that I wanted at a certain time, I wanted X to die, okay, and at this moment Y should be alive. So when Y is alive and X dies, Y will get a payment of £1 continuously as long as she is alive. Okay, so she'll get it from this point to her death. So the way of expressing this in terms of expected present value is basically going from 0 to infinity. What do I want? The first thing I want is obviously this is the all these possibilities can go from 0 to infinity. I need to fix the time of death of X. Okay, so in order to fix that, I need to select an arbitrary time t. Let's select a time t. So till this point of time, I want X to live, and then I want X to die at this time. Okay, this is something I want. Now what I want is at this time I want Y to be alive. So this becomes TPY, right? And we have obviously got a DT here. Okay, so I want X to die and I want Y to be alive. Now the third thing I want is what would be the amount of payment that would be made to Y from this moment on. See, by this time the age of Y would be Y plus T, right? Since we started from time 0 and we have reached time T. So the age of Y is Y plus T. So the payment that would be made from this age Y plus T till the death of Y can be modeled as a whole life continuous annuity. So it would be written as A continuous Y plus T. That is what you can write it as. Okay. So that's how you model it. And obviously I want to discount this payment from time T to back to time 0. So this becomes Vt. There is a factor Vt multiplied. Okay, I'm demonstrating this again. I think there would have been a confusion. Let's clear this. So what I want is I want X to live. I want to find an arbitrary time t from time 0 to infinity, right? So I have to add up all the possibilities. First, I want this is the time of death of X. This is when the payment starts. So till this time, I want X to survive, and then I want him to die immediately. Mu X plus T. Okay. Then what I want is I want Y to be alive at this time. Okay. And when Y, if and when Y will be alive at this point, I want to make a continuous payment from here till the death of Y. So now the age of Y is already Y plus T. So this becomes a continuous Y plus T. And obviously I'll be discounting this payment from this moment till time 0. So that becomes Vt and dt. Okay, even if you just understood it and you can't remember it right now, you'll be doing a lot of such similar intuitive reasoning based proofs soon. So you will actually get acquainted with this formula. Okay, so there is no issue about it. The symbol, the actual symbol for this kind of an annuity is called as A continuous X given Y. Okay, so basically I read it as X given Y, otherwise it's just X bar Y or whatever you can call it. Okay, this just says that I want to pay Y from the death of X till the death of Y, right? So I'll be paying making a certain payment to Y after X dies, right? And this payment would be in form of a continuous annuity. So this is how you derive this. Okay, so this is one definition of this EPV of a reversionary annuity that is payable from the death of X to the death of Y, right? There is one more definition of it, and you can actually prove an equivalence between this definition and that definition using the product rule of integration. So I'm not doing that proof here. I'm just going to give you that definition. If you want, you can try that proof, and if you don't get it, how these two are equivalent, just let me know, message me personally, and I will give you the proof, although it is not at all required for the exam. Okay, so let's just write the other definition. So it is A continuous X given Y, right? This is equal to going from 0 to infinity. What do I have here? See, the condition was that I will be paying from the death of X. So X has died okay, till the death of y. So y is alive during this entire tenure, okay. So y dies here, okay. So I am paying an amount from the death of x to the death of y, and there is no time constraint. It can be from 0 to time infinity, right? So rather than thinking about this entire payment as an annuity, we can actually look at this as as a sum of infinite number of payments that take place during this time, and each of this payment has to be discounted back till basically it has to be discounted back till time zero, right? So you can actually think of it as infinite payments that are happening between these 2 points, okay. So the way we can actually express this in terms of an integral is that we want to make a payment, okay. So the payment has to be of £1. I'm writing £1 here, although it has no relevance because multiplying anything with 1, it has no relevance, okay. When do I make this payment? I make this payment, these payments, all these payments between this point and this point, as long as y is alive. So at all these points which I'm considering, let's call all these arbitrary points t, okay, and at all these points I want y to be alive. So I can write this as tpy, right? So at all these points y is alive. I'm adding between 0 and infinity for all the conditions that y is alive. Also at all these points x is dead, so I can write as tqx, right? So at all these points I want x to be dead. So as long as y is alive and x is dead, so that automatically eliminates all these conditions, okay. It eliminates all these conditions and we are just left with this bracket, okay. So at since we are adding between 0 and infinity, we have removed these conditions and we are just left with this particular part we want, okay. So between these 2 points what I want is, as long as this thing is happening, there would be payments of 1 unit happening per annum, obviously, and these payments would be required to be discounted back till time zero. So far what has been the time at all these times t, the so far the time has been t years, right? So I'll have to, in order to discount them back to time zero, I'll multiply with the factor vt. So I'll multiply with the factor Vt and D2. So this is your simpler definition of this kind of an annuity. Going reversionary annuity, going from 0 to infinity, as long as y is dead, y is alive and x is dead, I'll be making payments which are discounted back till time 0 into D2, right? So you can think about it this way, and actually these two definitions are equivalent. Whichever one you apply, you will be getting the same answer. It's just that this is a simplified version, and this definition can be used to actually derive the definition which can be used to calculate the value of these reversionary annuities from the tables, right? So how will we do that? See, this says going from 0 to infinity, a continuous x given y is equal to, going from 0 to infinity, tpy into this tqx can be written as 1 minus tpx, okay, and into vt into dt, right? That's what I have. So going from 0 to infinity, if I separate these two terms, this becomes tpy into vt, minus going from 0 to infinity, tpy into tpx into vt dt. Now if you see this properly, this is the definition of a annuity that is payable as long as x is alive, so that becomes a continuous, as long as y is alive, so that becomes a continuous y, minus this is the definition of an annuity which is payable as long as both of x and y are alive. So this is a joint life annuity, so a continuous xy. So this is your final definition. A continuous x given y is equals to a continuous y minus a continuous xy. Right? That is how you can actually express this definition that we have. Okay. And another way of actually simplifying it more is, this can be written as 1 minus um, 1 minus a y, a immediate y over delta, right? And this can be written as minus, this is the premium conversion formula that I'm applying, okay. So you should remember this. 1 minus A continuous xy over delta, and if you simplify this, this becomes A continuous xy minus A continuous y over delta. So this is one more way of expressing this. So we have got so many results. Keep referring to the core reading here. See, they've given all these results in a similar fashion. They've skipped a few things which are required to connect them. So I've connected everything for you, okay, and derived everything. Okay. So these are a few ways you can deal with these things, right? So okay, that's cool. So what I just concluded is that A continuous x given y can be written as A continuous y minus A continuous xy, right? So this is the EPV of a reversionary annuity that is payable from the death of x to the death of y. So I take the life which has to be alive while the payments are happening, minus I have to take the joint life of both. Okay, so that is how you can represent this. In a similar fashion, A continuous y given x, that is the EPV of a continuous payment of an annuity which is happening from the death of y till the death of x, is obviously A continuous x minus A continuous xy. So this is how you can go about expressing these. If I get into the cases, discrete case, okay, so instead, now if the payments are happening, instead of happening at the continuously, now the payments are happening maybe, let's say, at the end of the years, right? We will take the advanced case too, everything would remain the same mostly. So now what is happening is, between the death of y, sorry, between the death of x and the death of y, I'll be paying at the end of every year a certain amounts, right, going from 0 to infinity. So if I were to express this in terms of a present value random variable, again, how can I write this? See, what I want is, it would be an annuity going from here to here, right? And what would be the amount of how many payments would have been there in this annuity if it is of £1? I'll have the number of payments would be just be the difference of the curate lifetime of y and the curate lifetime of x. For example, if x dies at the end of at maybe, let's say, 5.5 years, right? Okay, and y is dying at, let's say, maybe 10.5 years. So curate lifetime of x becomes 5. Okay, so how many payments would have happened? Let's just count that. Okay, so from 5, I'll have one payment at 6, one payment at 7, since the payments are happening at the end of the year. Okay, so one at 6, one at 7, one at 8, one at 9, and one at 10. And that's all. I would have had 5 payments, right? Because after 10.5, the payment at time 11 wouldn't have happened, because Y would have already been dead, and I would have no one to pay to, right? So I am providing financial security to Y, so Y has to be alive. So basically, there would have been 5 payments. So if I were to express this, this can be written as, the number of payments can be expressed as the curate lifetime of X minus the curate lifetime of Y. So what is the sorry, the curate lifetime of Y minus the curate lifetime of X. So what is the curate lifetime of Y here? The curate lifetime of Y is basically 10.5 is the exact lifetime. So the curate lifetime is equal to 10, and the curate lifetime of X is 5, obviously. So what is ky minus kx is equal to 5. So there are 5 payments as we expected. Cool. So this can actually be written as, and C. So this can be written as the annuity A ky minus kx, right? And since I need to discount this annuity from the death of x basically till time 0, Okay, so I've calculated the value of these annuity at time 5 basically. That is the curate lifetime of X. At this moment is when I've calculated the PV of this annuity, right? Because I've discounted it using a A5 annuity, and since the payments are in the at the end of the year, so 6, 7, 8, 9, and 10, all these payments have been discounted to time 5, right? So I'm at time 5 right now. Now I need to get it to time 0, right? So I multiply with a factor of V5, obviously. So how can I express this V5? This can be written as V to the power of KX, right? That's how you can write it. So this is your present value random variable, and this is applicable only if the lifetime of y, that is ky, is greater than kx, and otherwise, or maybe greater than equal to. I can take both the cases. Okay, not let's not include the equal to case here. Okay, this is only applicable if ky is greater than kx. Okay, and it is 0 otherwise. So if ky is less than equal to kx, so even if y and x die in the same year, that is the case when ky is equal to kx, there is no payment, because the first payment would have been at the end of the year when x dies, right? That is when this time 6. And if kx is equal to ky, that means y would have died between time 5 and 6. So by this time y would have already been dead, so there would have been no payment, thus it is included in this 0 case. Okay, I hope you understand that. Okay, so basically this is saying that I will pay this annuity a ky minus kx into v to the power of kx if ky is greater than kx, that is y lives for more than x, right? And if y dies in the same year or before x, there would have been no payment. So that makes a lot of sense, right? So it does. Cool. So the other ways I can express this again, if you will notice, this can be written as a maximum of ky minus kx comma 0, that remains the same. And the third way is obviously a ky minus a kx if ky is greater than kx, and 0 if ky is less than equal to. Okay, so now let's just move on to calculating the EPV of this contract. Okay, so we have to calculate the EPV a x given y, right? So this would be the EPV of all the payments of the annuity which would be payable from the death of x to the death of y, right? So this becomes like before ay minus axy. So the formula remains the same as in the continuous case. It's just that we basically have we do not have the continuous annuities, rather we have annuities which are payable in arrears. And this can also be expressed in this form like we did in the last part, axy minus ay, of course, upon d this time. I just applied the premium conversion formula here, so you can just do that. Okay, so what is this formula basically saying? Okay, let's try to intuitively understand this formula. So this is saying that if you want to calculate the EPV of all the pin of the this annuity, okay, this annuity which is being paid from the death of x to the death of y, what you're doing is you are taking the annuity which is payable till the death of y, okay, that is this, and you're deducting from it the EPV of the annuity while both of x and y are alive. So you are just basically, see, we know that both are alive here and here only y is alive. Okay, that's something we know. So what we are doing is we are taking the entire thing, that is when y is alive Okay, that annuity, that's the annuity we are taking, that is payable in at the end of every year as long as Y is alive, and out of that we are deducting the condition till here, that is when both of X and Y are alive. So we get this part where only Y is alive and X is dead. So that's what we need, right? So this formula makes intuitively a lot of sense. So that's something we have here. Now you can also have this version of the formula, A due X given Y. So now if you want to calculate the EPV of this becomes obviously A due Y minus A due XY. So that's how you can actually calculate this. Okay. Now let me just show you something here. Actually, A due X given Y is basically the same as A X given Y. These two things are equal. That is the annuity payable from the death of X to the death of Y in advance is the same as the EPV of the annuity which is payable from the death of X to the death of Y in arrears. If you want to prove this, let's start from the LHS. So this just becomes A due X given Y. So that becomes A due X, sorry, yeah, A due Y minus A due XY, and this is equal to A Y plus 1. That's how I can convert an annuity into a annuity payable in arrears into an annuity payable in advance. Okay, minus AXY plus 1, right? So these two plus ones cut out and this becomes AY minus AXY, which is the same as AXY, right? So these two things are basically equal, and that is something you should know. And if you think about it very logically too, in accordance with the number line, they turn out to be the same thing. I'll show you why. For example, here X dies and here Y dies. Okay, and I need obviously the EPV at the beginning of the year when X is dying. Okay, so right. So let's say X dies at time 5.5 and Y is dying at time 10.6. Okay, so what would be the amount of payment that would be made to them in this case, right? So if I consider the payments in advance, the payments would be made at the beginning of each year. Okay, so when will these payments start? They will start obviously at time 6, because at time 5 we couldn't have paid anything because X has died at 5.5. So time 5, time 6, I'm paying at the beginning of the year. Sorry, time 6, time 7, time 8, time 9, time 10. So I paid in advance at the beginning of all these years at the same time. Even if I would have paid at the end of the year, that is in arrears, and I don't pay anything after time 10 because Y is dead here. Again, if I pay in arrears, I would have paid at the same times because they are this after 5.5, next end of year occurs at 6, then next end of year occurs at 7, then 8, then 9, then 10. So effectively, there is no difference between these two annuities, and you can actually use either one of these, right? And the formula remains the same, right? So let us just take up a question here so that things are clearer. So we are taking the example that is given in the co-reading in this section. This is the example which is given on page 15 of my co-reading. Okay, so it says they want us to calculate a 65 given 60, right? Using the PA92C20, that is PMA92C20 and PFA92C20. using 4% per annum interest. They want us to calculate this using the PA90 to C20 tables and 4% per annum interest, assuming that there are two cases. If the life age 65 is a male and the life age 60 is a female, right? And the second one is the opposite, that is 60 is female, sorry, 65 is female and 60 is male, right? So in these two conditions they want us to calculate the expected present value. Amazing. So the first one I'm calculating is 65 given 60, where this is the male and this is the female. So you can actually write M and F over these. Okay. So what would be the value of this? This becomes obviously a due. I can use anything due or arrears or anything, since due is directly given in the tables. I'll be using that. Okay. So this becomes a due 60 minus a due 60 65 60. So this is male and this is female. So I actually need to calculate these values from the using the tables. Okay, so let's just see what are the values. Right. So I need A due F at 60. So A due F at 60 is equal to, see, we have got this at page number. Let's just find out the page number. The page number is I suppose 114. Okay. So I've got 114 of the tables and I want A due F60. For the female I want it at 60. So this is 16.652. Okay. So this is what we'll be using. And the other thing I want is, let's just rotate this. Can we rotate this? Okay, let's rotate this. Cool. This is what I have, right? So here I've got the male is 65 and the female is 60, right? So this says that whenever you want to find the value of the joint life annuity, and the male is X and the female is Y. So I want X to be 65, okay, and I want the female to be 60, that is 65 minus 5, so that is 12.682. So that is the value we use. Okay, so these are the two values that you can actually put in there. Let's put these values. This becomes 16.652 and this becomes 12.682. Okay, so this becomes 3.970. The values they're used in the book is 15.652 and 11.682, and they're basically the same. They've just used the arrears value and we've used the advanced values, and we just proved that they are exactly the same thing. So no worries about that. Okay, let's see the other one. The second part asks us to calculate a 65 given 60, where 65 is the female and 60 is the male, right? So this becomes a due 60, that is the male, right? And minus a due 60 65, this is the male, this is the female, right? So let's check out these values from the tables. So I want, what do I want? I want the, again let's just rotate this, rotating counterclockwise, right? So this is what I have, and now I want the male to be 60, right? So in the male 60 I've got 15.632. right? So if the male is 60, I've got 15.632. That is the value I have to use. And for the joint life annuity on the next page, on the very next page, 115. Let's just rotate this now again. Yeah. So I've got the male is X, so I want 60, and the female is 65, so plus 5, so 13.101, right? So let us just put these values there again. So this just becomes 15.632 minus 11.101, right? No, sorry, 13.101. So 13.101. So this becomes 2.531. And that is your answer, and that is how you calculate the value of these annuities. Okay, so now we are going to discuss something new, and this thing should have been included in chapter number 8. I don't know why they have included it here. So they have included it here, so I'm discussing it here. Okay, so let's just start talking about this. What would happen to joint life, term assurance, endowment assurance, and temporary annuity? See, so far we have talked about only whole life contracts, whole life assurances, and whole life annuities in case of joint life status and last survivor status. That is what we had talked about in the last chapter. Now, if I want to calculate the expected present value of a term assurance for two lives, for example, let's say I've got two lives that are X and Y. Okay, I've got these lives who are alive at this time, and I want to issue a term assurance. So within this is a n-year assurance, and within this term, if the joint life status fails, that is either one of X or Y, either one of X and Y, one of them dies here, okay, dies here, I'll be making them a payment of, to begin with, let's say £1, right? And if they die here, there would be no payment. So this is what I'm seeking here. I want to make a payment of £1 if they die here, and if they die here, there is no payment, right? So it seems very logical. Okay. Now let's just try to evaluate what would be the value of the term assurance, endowment assurance, and temporary annuity. This is something I was talking about was term assurance. Okay, so term assurance. So this is a term assurance where I want to make the payment to X and Y as soon as one of them dies, but this has to occur within n years. So there is a fixed term to this contract, and if this death occurs after n years, I don't care about it. So if I were to calculate, and this payment is immediately on death, let's assume this is immediately on death. So what would be the value of the EPV of this contract? The value of EPV of this contract is going from 0 to n. What I want is, I want X and Y both to survive at some arbitrary time t, till some arbitrary time t, which is of course between 0 and n. So I want X and Y both to survive. So TPX into TPY, right? I want both of them to survive. And then I want either one of them to die, right? So that is mu X plus T plus mu Y plus T. So X or Y. Okay, this is X and Y. I want both of them to survive and then one of them to die. And when this happens, there is a payment. Obviously, DT is there. There is a payment that is discounted back till time 0. Okay, from time t, of course, it is discounted back till time 0. So I've got a VT factor here. This is how you calculate the EPV of this contract, and this is denoted by the symbol AXYN with a 1 over both of these things. So I've got a 1 here over both of these things. This denotes that a payment is only made if this status fails first rather than this. Okay, and if I talk about the corresponding endowment assurance, for that I'll need the pure endowment part. Okay, pure endowment. So the pure endowment relating to this joint life status would say that X and Y both have to survive till time n, then and only then they will be made a payment of £1. So what would be the condition here? So the EPV can be written as probability that X survives till time n and probability that Y survives till time n. So there will be a payment Vn. So that is how you can basically denote this, or this can be simplified to be written as NPXY into Vn. Right. So that is your pure endowment contract in this case. Right. So normal joint life pure endowment contract. So if I talk about the endowment assurance here, it is obviously a sum of the pure endowment plus the, it is the sum of pure endowment plus the term assurance, right? So this one can be written as AXYN with a 1 over this, because if n years expire first and both of them survive, then and only then payment would be made. So this is denoted by the symbol AXYN, and this is just the sum of the above two. So that is AXY with a 1 over this n plus AXYN with a 1 over this. Okay, so that makes sense, right? So that's about the endowment um, assurance contract, and this was obviously immediate, and we can actually, this was also immediate, all of these were immediate since I was making the payment immediately on death, right? So I can also extend this argument to the contracts which make payment at the end of the year of death. So that says AXYN is equals to AXYN with a 1 over this plus AXYN with a 1 over this. So that's how you can extend this argument. Talking about the temporary annuity now. So temporary annuity payable continuously. First case, that is what I'll address, continuously. Okay. So let's just see that in the form of an integral. A continuous x, y, n. That is what I want. That is the EPV of this contract. See, this would be saying that as long as the joint life status is active, that is both of x and y are alive, both of them are alive, a payment is continuously made, but for the maximum of n years. So as long as x and y are alive till whatever time, but till a maximum of n years, payments would be made and they would need to be added and discounted back till time 0 if we need the EPV. So this is the EPV, and this would say going from 0 to obviously n, because maximum time we can make the payments is till n. Till this time what I want is the payments would be made as long as x and y both are alive. So TPX into TPY, I'm deciding some arbitrary time t, okay, and as long as these conditions are satisfied, the payment would be made, and this would need to be discounted to till time 0. So I'm adding all these possibilities, multiplying with Vt to discount it till time 0 and dt. So this is your EPV in this case, right? So that is something you should know. Okay. So now getting to how will you calculate these EPVs. See, you can extend the old single life formulas to these EPVs as well. So I'll be discussing the calculations. Okay. So how will you calculate these EPVs? First of all, what I had was the term assurance, right? So that is just now I'm discussing the discrete case where the payments are made at the end of the year of death. 1n. How can you calculate this? This just becomes AXY minus NPXY into V to the power of n into AX plus n y plus n. So that is how you can calculate it. AXY minus the probability that x and y both survive for n years into this factor, that the assurance that would start n years later, and you're just deducting this discounting this back till time 0. So the usual formula that we apply. Okay, this is the whole life assurance minus the deferred assurance, deferred joint life assurance. So that's what we're using. Okay, and how will you calculate the temporary annuity? For a temporary annuity you have AXYN. Okay, so this just becomes A due XY minus NPXY into Vn into A due X plus N Y plus N. Cool. And this factor NPXY into Vn, this can be calculated as obviously Lx plus N over Lx into Ly plus N over Ly into Vn, right? That's how you can actually calculate these two factors, right? So that is relating to the calculation. Now, how will you, let's talk about the last survivor status. Last survivor status, you have to always use the formula single plus single minus joint, right? For all the EPBs, you can use this formula directly. So if I talk about the term assurance in this case, or the endowment assurance, for the endowment assurance, it becomes AXY bar over it, N is equal to single plus single minus joint, that is AXN plus AYN minus AXYN, right? So single plus single minus joint. For the temporary annuity, our term assurance, it's just AXY bar over it 1N is equals to AX1N plus AY1N minus AXY1N, right? So that is how you can calculate this. For the temporary annuity, okay, so now talking about the temporary last survivor status annuity, that is A due XYN. Now there is a bit of a confusion with this particular kind of an annuity. The reason for this confusion is that is students try to evaluate using using a wrong formula. See, in this case, you can actually apply single plus single minus joint directly. How will you do that? That becomes A due xn, right, plus A due yn minus A due xyn. So you can use this formula directly. But the confusion is that you cannot use this formula. You cannot write this in form of a whole life last survivor annuity minus Vn into Npxy into A due x plus n y plus n, and this is a last survivor annuity. This formula is not at all correct. You cannot write a temporary last survivor annuity in this form. And the reason for this formula not being correct is that if I buy, for example, if I sell X and Y to people a last survivor annuity for n years, okay, so this will keep on paying them an amount of maybe of £1 as long as either of X and Y are alive, either is alive, right? So if X is alive, then only it will keep on paying. If Y is alive, then also it will keep on paying, and if both are alive, then also it will keep on paying. So at the end of n years, basically here we are assuming that this um, joint life, this last survivor annuity, this if we are deducting this part from it, we are assuming that this last survivor annuity will remain a last survivor annuity, but this is not true. At the end of the n years, three things can happen. Okay, three things can happen. It can so happen that by this time n, only x is alive and y is dead. It can so happen that only y is alive and x is dead. And it can so happen that both are alive. Okay. And in these different cases, this annuity will behave differently. In case only x is alive, this last survivor annuity is still payable. This would have still been payable as long as X is alive and he does not die, right? So it just becomes a single life annuity. In case of Y, only Y is alive, this would have become a single life annuity which would have been contingent upon the death of Y. And in case of both of them being alive, then and only then this would have stayed a last survivor annuity, right? So this becomes a single annuity, right? And in this case also it becomes a single annuity, and in only in this case this stays a joint um, a last survivor annuity, right? So there are basically three cases, and in this particular formula, we just assume that one of the cases that it would be only a last survivor annuity at the end of the n year. So instead of using this, actually you can use another formula. Although the best thing to use is the single plus single minus joint formula, but in case you do not you want to understand why this formula is wrong, then you can use this formula to see. This will help you understand. This becomes a du xy bar over it n is equal to a du xy. This is what I had already. This is the whole life annuity minus. Now there can be three cases. The first case can be that x survives and y dies. npx into nqy into Vn, right? So in this case, this becomes a single life annuity of x who is now aged x plus n. So this becomes a du x plus n now. In case only y survives and x dies, this becomes npy into nqx into Vn into a du y plus n who's aged y plus n. And in case both of them are survive, then and only then this will still remain a last survivor status annuity. So that just becomes a du x plus n y plus n with a bar. So this is the actual formula that you could have applied, but that formula is totally wrong. And this is what they have asked us in question number. They've asked us this in question number 9.15. Okay, so this is the formula that you could have applied, okay, if you wanted to. That formula is totally wrong, but instead of applying both of these formulas, this is a complicated one and that is the wrong one. We will just directly apply single plus single minus joint, and that would give us our answer in every case, right? So instead of doing all this hassle, you can just apply this formula directly and you will get your answer. So you just need to calculate a temporary annuity for X separately, a temporary annuity EPV of a temporary annuity for Y separately, and deduct the EPV of the joint life annuity. So now what I have next is I have to solve a question and then we'll be done. Okay, so let's just do this. Okay, so the question is a 60 60 with a bar over it 5. Okay, so it's asking us to calculate the the last survivor uh, endowment assurance function for two lives which are age 60 for 5 years, right? So this just becomes a 65 plus a 65. This is question number 9.14. This becomes a 65 a 65 and minus a 60 65. So that is how you can actually calculate this function, the value of this function, right? And this can be evaluated separately, this can be evaluated separately, this can be evaluated. So they are asking us to just express this in terms of this joint single and joint life annuity. So you can actually write this as 2a65 minus a 60 65, right? So that's what you can do as an end result. Okay, now there is question number 9.16 that we have to do. This is an interesting question. Let's just do this. So this would give you a lot of clarity about things. Okay, so it's asking us to calculate 9.16. We have to use the PA92C20, that is both the males and the females table, with 4% per annum interest. You have to use this table and calculate A5050 with a bar over it, that is the last survivor status, and 20, right? So the term is 20 years, and one life is male and the other life is female, right? So this is what you have to calculate. So this is probably M and this is F, right? So there are basically two ways of calculating this. Okay, um let's just I'll show you both the ways. Okay, so the first way of calculating this is you can actually use this a due single plus single minus joint. That is the easiest way. So a due 50/20 for the male, okay, plus a due 50/20 for the female, right? And minus the joint, that is a due 50 50 20, right? One for the male, one for the female. So that is how you can actually calculate this. In order to evaluate this, this becomes a due 50 for the male minus a due 70 for the male into L 70 over L 50 both for the male and V20, right? This is one thing. Same for the female, you have got a due 50F minus a due 70F into L 70 upon L 50 into V to the power of 20, right? And minus a due 50/50, that is the joint, one male, one female, minus a due 70/70, that is both of them live for 20 more years, and then I have to deduct this, that is the joint life, into L 70 over L 50, that is for the male, and this one L 70 over L 50 for the female into V20. Now when you will evaluate all these expressions, you will get the answer. So just go on and put the values and check the solution that they have given, and you should get the answer. Okay, this is one way of doing it. The second way of doing this is, if I am to calculate a due 50/50 20, okay, the other way is you can actually use the three cases which I told you. Okay, so after 20 years, what this is a last survivor status annuity. This will keep on paying as long as either one of the lives is alive. So 20 years later, three things can happen. One thing is X is dead and Y is alive. The other one is X is alive and Y is dead, and both are alive, right? So these three cases can be, and in this case, this becomes a single life annuity for Y, this becomes single life annuity for X, and this stays a last survivor status annuity for X and Y both, right? So that those are the three things that can happen, right? So I can actually write this as a due 50/50, that is what it is right now, minus what you can have here is the three cases. So the three cases are probability that X lives for 20 years, that is the male lives, and the female dies, that is 20q 50, okay, and v to the power of 20. And this makes this annuity now a single life annuity for X. So that is A due 50F. Minus the other one becomes 20p 50 for the female and 20q50 for the male, v to the power of 20 A due. Okay, this was not 50, this was 70 for the male. This becomes A due 70 for the male. Okay, so this has become a single life annuity only including X now. Okay, now this becomes a single life annuity only involving Y. Okay, and the third case, both of them survive. So 50M 50F, both of them survive for 20 years. Obviously V to the power of 20 and A due 70 70. So that is how you can divide it into three parts and calculate. And then what you have to do is you have to take this as A due 50 plus A due 50 minus A due 50 50. This is male, this is female, this is male female. That is, I'm applying single plus single minus joint in this case. You have to take all these cases, case 1, case 2, and in case 3 again you have to apply single plus single minus joint here. So this becomes 20p 50 m 50f v to the power of 20 into A due A due 70 m plus A due 70 f minus A due 70 70 mf. So this is the more complicated method of doing this kind of a question, which I would not recommend. Since I had to show you why this was the case, why there were three cases, is because there are three possibilities in this case. Otherwise, what you should do is the way I solved it in the first method, that is this formula, and then you just put your values here. Let me put the values and give you the answer. Okay, 9.16. So okay, so this part, it becomes, this is coming out to be, if you put the values, put all the values here, this comes out to be 13.940. This part is coming out to be 13.968, and the third part is coming out to be 13.780. So this is 13.780. Okay, and when you adjust these three, single plus single minus joint, okay, so the net answer that you get is 14.128. That is the answer that you need for this. So do practice this, and I would suggest using the first formula. The second one is a really tricky one, which you'll be able to master only over time. Okay, and you don't actually need it. So that's all for this video. Thank you guys, and in the next video I'll be discussing a topic called more complex conditions. So um, that is the most interesting part of this chapter, where they can actually make confusing questions, but we will be seeing the logic behind everything. So I think that should sort things out for you. So see you then. Cheers.